Somewhere right now, a billion electrons are streaming through the wires in your walls, igniting the lights above your head, powering the device in your hands, and dancing inside the very atoms that make you. We trust them to run our world. But if you tried to find one, really find it, you'd discover something unsettling. The harder you look, the less it seems to be there. Is it a particle, a wave, a ripple in an unseen ocean, or something stranger still? A phantom that exists only when we dare to look? Tonight, we chase the most elusive quarry in all of physics, the electron, the particle you can't pin down. We have built our civilization upon them. Every flicker of electricity, every chemical bond, every living thought in your brain, all are choreographed by the invisible presence of the electron. And yet, in more than a century of trying, not a single human being has ever seen one. Not truly, not in the way you might imagine. This is no ordinary invisibility, like a speck too small for the eye. This is something deeper, stranger. Electrons refuse to stay still long enough to be found. They smear themselves into clouds of probability, dissolve into waves, and sometimes vanish into the quantum vacuum itself, only to reappear somewhere else without crossing the space between. If you think you've cornered one, it will have already slipped into a form that mocks the idea of position entirely. It's a problem that gnaws at physicists, and perhaps at reality itself. If something so central to the universe's architecture resists every attempt to pin it down, what does that say about the nature of existence? What does it say about us? In the early days, we thought we had it figured out. The electron was imagined as a tiny sphere, a bead of negative charge, orbiting the atomic nucleus like a planet around a star. A neat, mechanical image, drawn from the comforting rules of classical physics. In school books, it looked almost like a miniature solar system. Predictable, graspable. But that image was a lie. The deeper we probed, the more the electron mocked our expectations. We built machines the size of cities, smashing particles together at nearly the speed of light, hoping to glimpse its shape. What we found was nothing. No hard edge, no structure, just numbers, mass, charge, spin, as if the electron were more a set of instructions than a thing. And stranger still, those instructions seem to be written into the universe itself, not tied to any one place or form. Imagine chasing a ghost through a fog that changes shape every time you shine a light on it. That is the hunt for the electron. And yet, despite its maddening elusiveness, the electron leaves fingerprints everywhere. It bends light in magnetic fields, sculpts the colors of the world through quantum jumps in atoms, and shapes the entire periodic table. It can be coaxed into flowing through a wire as a current, or trapped in a magnetic bottle for months, dancing to the tune of precise frequencies we can measure to 14 decimal places. We can't catch it, but we can hear its music with exquisite clarity. That paradox, the fact that we can measure an electron's properties with greater precision than almost anything else in physics, yet cannot say what it is, has fueled some of the deepest debates in science. Some physicists see it as proof that reality at the smallest scales is inherently probabilistic, a realm where questions like, "Where is the electron?" simply have no meaning until we ask them. Others suspect there is a deeper layer of truth, one we have not yet touched, where the electron has a hidden form, something more tangible but forever veiled from our present understanding. In the coming hour, we will trace the story of the electron from its discovery in the shadowy glow of a cathode ray tube, through the radical upheavals of quantum mechanics, to the modern vision of electrons as ripples in an invisible field that fills the cosmos. We will see how experiments like the double slit shattered our illusions of solid particles, and how quantum field theory replaced them with a far stranger picture, that the electron may be less a thing and more an event, a disturbance in the underlying fabric of the universe. We will also dare to ask the question that few in science openly confront. If the electron resists our every attempt to define it, can we even say it is real in the way we think of reality? Or is it perhaps a story we tell ourselves, a map of behavior with no territory behind it? This is not merely an academic exercise. Understanding the electron has been the key to nearly every technological leap of the last century. From transistors and microchips to lasers and quantum computers. If our picture of it is wrong, the implications for future technology and for our understanding of existence could be profound. As we set out on this journey, picture an electron not as a neat, predictable sphere, but as something fluid, evasive, and ungraspable. It might be a smear of possibility one moment, a ripple in an endless field the next, or a particle-like blip when cornered by an experiment. It is as if nature has placed the electron at the intersection of wave and particle, certainty and uncertainty, existence and non-existence, a trickster hiding in the shadows of physics. And so we begin in the final years of the 19th century, when a beam of mysterious light green glow in a vacuum tube revealed the first hint that the atom, once thought indivisible, had secrets to give up. But the men who first saw this ghostly stream of particles had no idea they were peering into a mystery that would challenge our most basic notions of reality for more than a century. The electron story is not just the tale of a particle. It is the tale of how, in chasing it, we were forced to confront the fact that reality itself might not be what we think. And the chase begins now.
The year is 1897. In a quiet laboratory at the Cavendish in Cambridge, J.J. Thomson peers into a glass tube glowing faintly green. It is a strange contraption, a sealed vessel from which the air has been pumped out, fitted with electrodes at either end. When a high voltage is applied, something invisible streaks from the negative end to the positive, producing a luminous glow where it strikes the glass. This was the cathode ray tube, a marvel of Victorian science and a puzzle.
What exactly were these mysterious cathode rays? Many believed they were simply waves in the ether, a kind of light with no mass. Others suspected streams of tiny particles, but no one had ever proved either theory. Thomson, meticulous and cautious, decided to measure their properties directly. His approach was deceptively simple. He placed metal plates inside the tube and applied electric and magnetic fields to the beam. If cathode rays were made of charged particles, the field should deflect them. And if they were particles, measuring that deflection would allow him to calculate their ratio of charge to mass. The result astonished him. The deflection was far greater than that of any known atom or ion. In fact, the particles were thousands of times lighter than hydrogen, the lightest known element. Thomson had found something new, a subatomic particle, far smaller than anything imagined. For the first time in history, the atom, once thought indivisible, had been cracked open. Inside there was a smaller building block, the electron. He could scarcely have imagined the chain of events he had set in motion. His discovery was not just a new particle, but the first glimpse of a hidden realm beneath the surface of matter. Until that moment, the universe seemed a clockwork machine built from solid, indivisible pieces. Now, that simplicity was gone. The press seized upon the idea, calling these newly discovered particles corpuscles. The name didn't stick. Electron, proposed earlier by the Irish physicist George Stoney, soon took hold. But the cultural impact was immediate. Suddenly, the atom was no longer the bedrock of reality. It was a nest of mysteries, and the electron was the first hatchling to emerge. Thomson himself, despite his groundbreaking work, imagined electrons embedded in a diffuse sphere of positive charge, the so-called plum pudding model. Electrons, like raisins, were suspended in a positively charged mass that made up the rest of the atom. It was a tidy picture, and for a time it seemed plausible. But the universe does not stay tidy for long. Other experiments soon began to chip away at this view. Thomson's own student, Ernest Rutherford, would one day fire alpha particles at thin gold foil and discover that atoms were mostly empty space, with their positive charge concentrated in a tiny, dense nucleus. That meant electrons weren't embedded in a solid mass at all. They were orbiting something incredibly small, but incredibly heavy. This revelation shifted the mental picture again. The atom now resembled a miniature solar system, a central sun-like nucleus with tiny electron planets whirling around it. It was elegant, it was simple, and it was wrong. Yet in 1897, those flaws were invisible. The excitement was too fresh. Imagine the intellectual thrill. A whole new layer of nature had been revealed. The atom was no longer the ultimate particle. It had parts. And those parts had properties. The electron carried a negative electric charge. It had a specific, measurable mass, and it seemed universal, the same in every material tested. Thomson's experiments even suggested that electrons were identical no matter where they came from. Whether freed from a chunk of metal or coaxed out of a gas, they behaved the same. This hinted at a deep, underlying unity, as if electrons were fundamental to the construction of everything in the universe. By the turn of the century, this revelation had electrified, quite literally, both science and industry. It explained the mysterious flow of current in wires. It promised a future in which electricity could be controlled, stored, and harnessed more efficiently. It hinted at a connection between matter and electricity that no one had fully understood before. And yet, from the very beginning, there were whispers of strangeness. Even in those early experiments, electrons didn't behave exactly as expected. Their motion was too agile, their interactions with light too peculiar to fit neatly into the picture of a tiny billiard ball. But those puzzles could wait. For now, it was enough that the electron existed. Looking back, it is remarkable how quickly the discovery of the electron became embedded in the fabric of modern life. Within a generation, it would underpin the entire field of electronics, a word that, of course, comes from electron. The light bulb, the radio, the telephone, and eventually the computer, all of them were, in a sense, the children of that glowing green beam in Thomson's laboratory. But while engineers learned to control electrons, physicists still did not truly understand them. They could measure an electron's charge and mass with extraordinary precision. They could predict its behavior in certain situations. But what was it really? Was it a particle, a wave, a combination of both, or something entirely different, hiding behind the mathematical symbols of their equations? In the first decade of the 20th century, these questions would explode into the open. The neat planetary model of the atom would come under siege from a series of baffling experiments, and each time physicists thought they had cornered the truth about electrons, the particles would change their shape, slip through the cracks of classical logic, and vanish into the mists of probability. But before that reckoning, there was a brief period, a scientific calm before the quantum storm, when the electron seemed solid and knowable, a true building block of matter. It is worth pausing here in 1897 to appreciate the weight of that moment. For thousands of years, philosophers had wondered if matter could be divided endlessly, or if there was a smallest piece. The ancient Greeks called it the atom, indivisible. In less than a decade, that dream of finality was gone. Matter was not made of indivisible atoms, but of smaller things still, and the electron was just the beginning. What Thomson had found was not simply a particle. He had found the key to a deeper mystery, one that would ultimately force humanity to question the meaning of existence itself. And the first cracks in our comfortable picture of reality were about to widen. The turn of the 20th century was an age of bold certainties. The world's great powers carved their borders on maps, railways stitched continents together, and science promised that all mysteries would soon be solved. In the laboratory, the newly discovered electron was being hailed as a triumph of human reason, a glimpse of the machinery beneath reality's skin. For a few short years, the prevailing picture was almost comforting. Atoms, once thought indivisible, now resembled miniature solar systems, a dense, positively charged sphere at the center, the Sun, surrounded by electrons, the tiny planets, circling in neat, predictable orbits. It was the plum pudding model that had given way to a more planetary vision. The nucleus, though not yet directly seen, was assumed to be diffuse, a kind of glowing orb of positive charge with electrons embedded or drifting within it. This image satisfied both physicists and the public. It was elegant, it was mechanical, it felt right. And then came the gold foil experiment. In 1909, Ernest Rutherford, along with Hans Geiger and Ernest Marsden, sought to probe the structure of the atom more deeply. They fired alpha particles, heavy, positively charged bullets from radioactive decay, at an impossibly thin sheet of gold foil. The reasoning was simple. If the atom's positive charge was spread evenly throughout, the alpha particles should pass through with only slight deflections, like cannonballs through mist. For days they watched through detectors. As expected, most alpha particles sailed straight through untouched. But then came the shock. Some particles veered at sharp angles. A few, just a few, bounced straight back as if they had struck something solid. Rutherford later remarked, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." This was no diffuse positive sphere. The atom's mass and positive charge were concentrated in a tiny, dense core, the nucleus. Around it, the electrons were not embedded, but somehow kept their distance, bound by electric attraction. The planetary model now seemed irresistible. Electrons orbited the nucleus like moons around a planet, their motion keeping them from spiraling inward. It was a beautiful analogy, so beautiful, in fact, that it blinded many to the trouble it contained. Because according to classical physics, electrons in orbit should constantly radiate energy as they accelerate around the nucleus. This radiation would drain their energy, causing them to spiral inward in a fraction of a second, collapsing the atom entirely. Yet atoms stubbornly refused to collapse. The world, and its matter, endured. Here, in this contradiction, was the first clear sign that something in our understanding was fundamentally wrong. It was the Danish physicist Niels Bohr who stepped into the breach. In 1913, Bohr proposed a radical solution. Electrons could occupy only specific orbits, each with a fixed energy. They did not radiate energy in these allowed orbits. Only when they jumped from one orbit to another would they emit or absorb light in discrete packets called quanta. Bohr's model was revolutionary. It explained the discrete spectral lines seen in hydrogen's light, each corresponding to an electron moving between energy levels. For the first time, quantum ideas, still new and unsettling, were woven into the picture of the atom. The public embraced Bohr's model. School diagrams of atoms became little solar systems, complete with electron planets in perfect rings. The analogy was irresistible, a universe within a universe, the macrocosm mirrored in the microcosm. But beneath the elegance, the questions deepened. Why could electrons only occupy certain orbits? How did they know when to jump? And what determined their paths between these states? When physicists tried to calculate the electron's exact position and momentum at the same time, they ran into problems. The math rebelled. Electrons were not behaving like tiny billiard balls at all. It was as if the more we learned about the atom, the less solid it became. The planetary orbits gave way to the idea that electrons formed a kind of cloud, a haze of probability spread out over space with no definite location until measured. The Bohr model, though a giant leap, was only a stepping stone towards something far stranger. Still, in these early decades there was a feeling of progress. The nucleus was real, electrons were real, or so it seemed. We could measure their charge, their mass, their behavior in magnetic and electric fields. We could even coax them into drawing images, as in the newly invented cathode ray displays. It felt as though we were on the verge of complete understanding. And yet, lurking in the shadows was the experiment that would shatter that confidence. An experiment so simple in concept, yet so profound in implication, that it would force physicists to abandon the very idea of an electron as a solid particle. It was an experiment with slits, just two slits, and electrons would reveal through them that the universe does not work the way common sense says it should. We are about to walk through that slit. By the 1920s, the electron seemed both indispensable and comfortably familiar. It was the cornerstone of chemistry, the workhorse of electricity, the very glue that bound atoms together. The Bohr model, with its tidy orbital rings, adorned textbooks and lecture halls. Engineers had harnessed the electron to create radio, early television, and powerful new instruments. Yet under the surface, the Bohr model was under siege. The trouble began with light. According to classical theory, light should behave only as a wave. But Einstein's 1905 explanation of the photoelectric effect, in which light knocks electrons from a metal surface, required light to act as if it came in discrete packets, photons. If light could behave as both wave and particle, could matter itself do the same? It was Louis de Broglie, a French aristocrat with the manner of a poet, who made the audacious suggestion, if light, a wave, can behave like a particle, then perhaps electrons, particles, can behave like waves. He proposed that every particle of matter has a wavelength, inversely proportional to its momentum. The idea was bizarre. Waves spread out, interfere, diffract. Particles are localized, solid, tangible. To say an electron could be both was to invite chaos into physics. But de Broglie's theory was soon put to the test, and the results were undeniable. In 1927, Clinton Davison and Lester Germer at Bell Labs were studying how electrons scatter off a nickel crystal. To their astonishment, the electrons produced a diffraction pattern, the same kind of pattern made by light waves. It was the first direct evidence that electrons had a wavelength. The old, comfortable picture of electrons as tiny solid spheres began to fracture. If electrons were waves, what was waving? Was it the electron itself smeared out through space? Or was it something more abstract, a wave of probability, as some theorists whispered? The tension in physics was reaching a breaking point. The neat orbits of the Bohr model could not explain why electrons sometimes behaved like particles, sometimes like waves. They could not explain why certain measurements seemed to collapse the electron's spread-out state into a single point. And looming over all of this was an experiment so deceptively simple that it should have been unremarkable, but which would instead tear a hole in our understanding of reality. The double-slit experiment. Imagine a barrier with two narrow openings like twin doorways cut into a wall. On one side, you have a source of something. It could be water waves, light, or in this case, electrons. On the other side, you have a screen to record where they land. If electrons were purely particles, you would expect them to pass through one slit or the other, forming two distinct bands on the screen. If they were purely waves passing through both slits at once and interfering, you'd expect a series of bright and dark fringes, an interference pattern. So, which would it be? When scientists first tried the experiment with electrons, they found, astonishingly, that they produced an interference pattern. The electrons behaved like waves, each one somehow passing through both slits at the same time, interfering with itself. But then came the twist. Place a detector at the slits to see which path the electron takes, and the interference pattern vanishes. The electrons act like particles again, hitting the screen in two neat clusters. Remove the detector, and the wave pattern returns. It was as if the electron knew when it was being watched. This was not merely a technical curiosity. It was a deep wound in the heart of classical thinking. How could the simple act of observing change the outcome? The electron's behavior seemed to depend on the possibility of knowledge, not just on physical forces. Some physicists embraced this strangeness. Niels Bohr argued that at the quantum scale, reality is not definite until measured. The electron does not have a location or a path until an observation forces it to choose. Others, like Einstein, recoiled, suspecting that some hidden variable was at work, some deeper mechanism that restored the comfort of an objective reality. But no hidden variables have ever been found that can fully explain the results. In fact, later experiments have only deepened the puzzle. showing that the decision to observe can even be delayed until after the electron has passed the slits. And the interference pattern still vanishes retroactively, as if the past were being rewritten. The cracks in our picture of the electron had become fissures. It could no longer be neatly filed away as a particle or even as a wave. It was something else, something stranger, that defied both categories. And the double-slit experiment was only the beginning. In the years that followed, quantum mechanics would emerge to explain, or at least describe, this bizarre behavior. And in doing so, it would strip away our last illusions about what the electron is. Next, we step fully into that quantum world, a place where electrons are not where you think they are, not even when you think you're looking. Picture the scene: a darkened laboratory. At the far end, a glowing emitter hums softly, sending a faint stream of electrons toward a barrier with two narrow slits. Beyond the barrier, a phosphorescent screen waits to catch their arrival, each impact appearing as a tiny point of light. At first, the experimenters open both slits and simply watch. The electrons, flung from their source like tiny bullets, should strike the screen in two distinct vertical bands, each one aligned with a slit. That is what classical physics demands. But when the pattern slowly emerges, it is nothing like that. Instead, they see a sequence of alternating bright and dark fringes, an interference pattern, the unmistakable signature of waves overlapping and cancelling each other. Yet there is no water here, no light waves. This is matter, electrons, each with mass and charge. And still, somehow, each electron seems to have passed through both slits at once, interfering with itself like a ghost playing both roles in a duet. The experimenters take a bold next step. They lower the electron stream so that the particles are fired one at a time, separated by seconds, even minutes. In theory, each solitary electron should simply choose one slit and hit the screen accordingly. But no, the interference pattern still forms. Even when fired alone with no other electrons to interfere with, each electron contributes to the same fringe pattern, as if it is aware of both slits and somehow, impossibly, is taking both paths simultaneously. This is not a fluke. Repeat the experiment 100 times, 1,000, 1,000,000. The same pattern emerges. The conclusion is inescapable. The electron's path is not a single defined trajectory, but a superposition of possibilities, all existing until the moment of measurement. And then comes the real shock. Curious to see which way the electron actually goes, the experimenters place a detector at the slits, a device to tell them whether an electron passed through the left slit, the right slit, or both. The result is instant and profound. The interference pattern vanishes. Instead, the electrons behave like tiny bullets again, striking in two neat clusters. The very act of measurement, of observing, changes the outcome. Remove the detectors and the interference pattern returns. Add them back and it disappears again. The electrons somehow know when they are being watched. It is one of the most unsettling moments in all of science. This is not a matter of disturbing the electrons physically with the detector, not entirely at least. This is something deeper. The electron behaves as though reality itself depends on the availability of information. In the decades since, the experiment has been refined, extended, and reimagined in countless ways. Photons, atoms, even molecules far larger than electrons have shown the same eerie behavior. Quantum mechanics gives us the mathematics to predict the results with astonishing accuracy. But the why, the mechanism, remains slippery. Niels Bohr's Copenhagen interpretation embraces the strangeness. An electron does not have a definite position or path until it is measured. Until then, it exists as a cloud of probabilities, a mathematical wave function that describes all possible outcomes. The moment of observation collapses the wave function into a single reality. Einstein, for his part, could not accept this. "Do you really believe the moon is not there when you are not looking at it?" he challenged Bohr. Yet repeated experiments suggest that at the quantum scale, this is exactly how nature behaves. Later variations on the experiment make it even more bewildering. In the delayed choice version, the decision to measure which slit the electron passes through is made after the electron has already passed the barrier. And still, the interference pattern disappears as though the electron retroactively adjusted its path to match the present conditions. This defies our most basic intuitions about cause and effect. It suggests that the electron's history is not fixed, but is instead contingent on the conditions of the present, on whether or not information about its path can exist. And here, the philosophical undertones deepen. If the electron's past is shaped by the present, what does that say about reality itself? Is the universe, at its most fundamental level, a tapestry woven from probabilities until the loom of observation snaps them into place? Some interpretations, like the many worlds theory, try to avoid the problem by suggesting that the electron takes all possible paths, but in separate branching universes. Others, like quantum Bayesianism, treat the wave function as a representation of our knowledge, not of reality itself, but none of these interpretations can claim a final victory. What is clear is that the electron is not what the early pioneers imagined. It is not a tiny marble orbiting a nucleus, nor even a smeared-out cloud in a fixed pattern. It is a player in a quantum drama, moving between the roles of particle and wave, depending on the rules of the scene. Rules that seem to depend on us, the audience. For over a century, the double-slit experiment has stood as both a triumph and a warning. It tells us that our equations work, but our understanding lags behind. That the deeper we probe into the heart of matter, the more reality behaves not like a clockwork machine, but like a story that changes depending on how it is told. And the electron, that most familiar of particles, sits at the center of the stage, smiling, if such a thing could smile, at our confusion. But this is only the beginning of the strangeness. For if the electron can be in many places at once until we look, what does that mean for its nature? Is it truly a thing at all? Or is it simply the visible crest of a much larger, invisible wave? To answer that, we must meet the man who gave the electron its most enduring mathematical description, and in doing so, redefined reality itself. The year is 1926. The physics world is still reeling from the implications of the double-slit experiment. Electrons, the very currency of modern life, are behaving in ways that make no sense in the language of classical science. Enter Erwin Schrödinger. Schrödinger was not an experimentalist. He was a theorist, a man of chalkboards and equations, with a mind tuned to the subtle harmonies of mathematics. In a feverish burst of work, he produced something astonishing, a single equation that could describe the wave-like behavior of any quantum object, from photons to, most importantly, electrons. It was deceptively simple in appearance, but its implications were profound. Schrödinger's equation didn't give you the electron's location directly. Instead, it produced a wave function, a kind of abstract mathematical wave. The peaks and troughs of this wave didn't represent physical crests of matter, but probabilities. Where the wave was high, the electron was likely to be found. Where it was low, the electron was unlikely. This was the true meaning of the electron's wave nature. It wasn't a solid object undulating through space, but a set of probabilities, a haze of potential positions. Until you looked, it existed everywhere the wave function said it could be. For many, this was an unsettling leap. In everyday life, probabilities describe our ignorance, not reality itself. If you flip a coin and hide it under your hand, it's either heads or tails. You just don't know which until you look. But in quantum mechanics, the electron isn't really there in one place waiting to be found. Before measurement, it genuinely exists in all the possible states the mathematics allows. Schrödinger's equation explained why electrons in atoms didn't spiral into the nucleus. Instead of neat orbits, electrons occupied orbitals, standing waves of probability that wrapped around the nucleus in specific shapes. Some were spherical, some were dumbbell-shaped, others more complex. These orbitals defined where an electron was likely to be found, but never fixed it to a single spot. It was a revolution in how we saw matter. The Bohr model's tidy rings gave way to clouds, diffuse, ghostly regions where the electron's presence was most probable. This matched experiment beautifully. Atomic spectra, chemical bonding, even the stability of matter itself all fell into place when described in this way. But there was a price. The picture was now stranger than ever. The electron was not a little ball circling the nucleus. It was a smear of possibility, an entity defined by mathematics, until forced into concreteness by observation. Niels Bohr embraced this wholeheartedly, declaring that quantum mechanics didn't just describe the world, it was the world at small scales. Albert Einstein remained skeptical, famously saying, "I like to think the moon is there even if I am not looking at it." But the mathematics refused to bend to Einstein's comfort. Every experiment agreed with Schrödinger's predictions. There was, however, one more twist, and it came from Werner Heisenberg. Heisenberg introduced the uncertainty principle, the idea that there is a hard limit to how much we can know about certain pairs of properties. For an electron, the more precisely you know its position, the less precisely you can know its momentum, and vice versa. This wasn't a flaw in our instruments, it was a fundamental property of nature. The uncertainty principle cemented the picture of the electron as unpin-downable. Ask where it is, and you lose track of where it's going. Ask where it's going, and you blur out where it is. This wasn't just practical inconvenience. It was telling us that the very concept of a fixed, definite trajectory was meaningless at the quantum level. If Schrödinger gave us the haze of possibility, Heisenberg told us why the haze could never be dispelled. The electron is uncertainty. It lives there, in that space between what could be and what is. And yet, despite this inherent vagueness, the behavior of electrons could be predicted with almost supernatural precision. The mathematics of quantum mechanics, armed with Schrödinger's equation, could forecast the outcome of experiments to something like 14 decimal places, more accurate than any other scientific theory in history. This created a strange duality. The more precisely we could calculate the electron's probable behavior, the less we could claim to know what it actually was. It was like knowing every note in a symphony, but having no idea who or what was playing it. Even the visual models of the atom had to change. No longer could we depict electrons as neat planetary orbits. Instead, textbooks began showing swirling, cloud-like regions, fuzzy but precise in their own way. Chemistry, too, was transformed. The shapes of molecules, the way they bond, the reactions they undergo, all emerged naturally from the probability clouds of their electrons. For the first time, scientists could explain why the periodic table worked, why sodium and chlorine combined into salt, why diamonds were hard, why metals conducted electricity. The answer was always in the orbitals, the patterns of probability in which electrons lived. And yet the philosophical discomfort remained. If electrons are just clouds of probability, what is actually there between measurements? Is the electron real before we look, or does our act of looking conjure it into being? Physicists learned to live with this question by adopting a pragmatic view. Shut up and calculate, as the saying went. The theory worked. It could be used to build transistors, lasers, atomic clocks, and even lay the groundwork for quantum computers. For practical purposes, that was enough. But the deeper mystery never went away. The Schrödinger equation told us how electrons behave. It did not tell us why. And for those unwilling to settle for silence, the hunt for the electron's true nature had only just begun. Next, we will step into the philosophical battlefield of the Copenhagen interpretation, where reality itself may be conditional, and the electron might only exist in the moment you decide to look. By the mid-1920s, the haze of probability surrounding the electron had become the centerpiece of a new scientific revolution. The mathematics of quantum mechanics worked. It predicted spectra, chemical bonds, reaction rates, even the behavior of exotic states of matter. But there remained the maddening question: what does it mean? Into this intellectual maelstrom stepped Niels Bohr. Bohr, already famous for his atomic model, was now convinced that the strangeness of the quantum world was not a flaw to be fixed, but a truth to be embraced. Alongside Werner Heisenberg, he crafted what would become known as the Copenhagen interpretation, an audacious, almost unsettling claim about the nature of reality itself. At its heart was a simple but radical proposition: the wave function, that shimmering mathematical cloud describing the electron's possible states, is not a description of an underlying physical object in space. It is a description of our knowledge of the system, and until a measurement is made, the electron does not have definite properties such as position or momentum. It is not in one place or going one way until we interact with it. Bohr argued that asking, "Where is the electron?" before I measure it was like asking, "What is the color of the wind?" A category error, a question that simply doesn't make sense in the quantum domain. The double-slit experiment was the perfect case study. When unobserved, the electron behaves like a wave, exploring all possible paths and producing an interference pattern. When observed, it behaves like a particle, passing through one slit or the other. Bohr's conclusion was that these aren't two contradictory realities, but two complementary aspects of the same underlying phenomenon, aspects that cannot be observed simultaneously. He called this complementarity. In the Copenhagen view, the electron is not a wave or a particle. It is something that transcends those categories, revealing itself differently depending on the question you ask and the way you choose to measure it. This was not just a new theory of electrons, it was a new theory of reality. Bohr's stance placed the act of measurement, and by extension, the observer, at the very center of the story. Without an interaction that counts as a measurement, the quantum world remains in a state of superposition, a spread of possibilities. The moment of measurement is the moment reality chooses a particular outcome. To some, this was thrilling. Physics was no longer just about cold, objective particles moving according to fixed laws. It was about the relationship between the knower and the known. To others, it was deeply disturbing, even unscientific. Albert Einstein, once Bohr's intellectual ally, became his most famous critic. At the 1927 Solvay conference in Brussels, the two men clashed repeatedly. Einstein attacked the Copenhagen interpretation as incomplete, famously declaring, "God does not play dice with the universe." Bohr, equally stubborn, replied, "Einstein, stop telling God what to do." Einstein's discomfort was not merely philosophical. He suspected that the wave function was a statistical tool, masking an underlying reality that was still deterministic, hidden variables that, if discovered, would restore certainty to the quantum world. But every attempt to construct such a hidden variable theory that matched quantum predictions failed to satisfy the experimental evidence. Meanwhile, the Copenhagen camp doubled down. Heisenberg's uncertainty principle became a central pillar. Not only can we not know an electron's exact position and momentum simultaneously, but there is nothing there to know until the moment of measurement. This was not a limitation of technology, it was a limitation built into nature. For the public, this was intoxicating. Quantum mechanics, and the mysterious electron at its heart, seemed to confirm ancient philosophical ideas about the role of the observer, the illusory nature of solidity, and the possibility that reality was not out there, but somehow entangled with consciousness itself. Bohr himself was careful, almost painfully so, about how far he extended these implications. He resisted mystical interpretations, insisting that quantum mechanics was complete, but limited to describing phenomena, not underlying reality in the metaphysical sense. The electron was not real in the everyday sense. It was a set of potential measurement outcomes, and nothing more. Yet even this restrained view carried staggering consequences. If the electron does not have definite properties until we measure them, then reality at its most fundamental level is not a solid, unchanging thing. It is a dynamic interplay between possibilities and events, between questions and answers. Consider the atom. In the Copenhagen interpretation, the electrons that give atoms their structure are not tiny marbles orbiting a nucleus, but probability clouds that have no precise location until disturbed. The stability of matter, the very fact that you can hold a cup of coffee without your hand passing through it, is a statistical phenomenon, a kind of quantum stalemate between the electron's tendency to spread out and the nucleus's electric pull. And yet we can build entire civilizations on this ephemeral foundation. This paradox, that something so foundational can also be so uncertain, is what gives the electron its peculiar allure. It is both the most familiar and the most alien of particles. It lights our homes and runs our computers, but it also refuses to be real in the sense our intuition demands. The Copenhagen Gambit did not end the debate. It hardened it. For decades, physicists would split into camps: the pragmatists, who adopted Bohr's view because it worked, and the realists, who sought a deeper, more deterministic explanation. But no matter which side they took, the electron remained the perfect symbol of the problem, a particle you can describe but not define, a thing that exists but not in the way you think. And while Bohr's camp claimed victory in the early 20th century, the battle over the electron's true nature was far from over. In time, a new framework, quantum field theory, would arrive to challenge even the Copenhagen interpretation, replacing the electron as particle or wave with something even stranger. But before we leap to that new vision, we must confront the experimental evidence that cemented Bohr's worldview in the minds of many. Tests that pushed the electron into situations where classical logic broke entirely, and where reality itself seemed to flicker in and out of focus. If the Copenhagen interpretation declared that the electron was defined by probabilities rather than certainties, then surely, the way forward was to probe it more closely. Build better instruments, push to higher energies, force the electron to reveal itself if only for an instant. For more than a century, physicists have tried exactly that. The earliest attempts came from scattering experiments. By firing beams of electrons at other particles and measuring the deflections, scientists hoped to infer the electron's size and shape. In the classical world, this is straightforward. Bounce a ball off a wall, and the angle tells you something about the wall's structure. Bounce a marble off a marble, and you can work out their dimensions. But when they did this with electrons, the results were baffling. The data suggested that the electron had no measurable size at all, consistent within experimental limits with being a mathematical point. The point-like nature persisted even as accelerators grew in power, hurling particles together at energies unimaginable in Thomson's day. It was as if the electron was not a thing with a boundary, but a set of properties: mass, charge, spin, anchored to a location that had no spatial extent. In technical terms, the electron's measured radius was less than a trillionth of a meter. If it has a size at all, it is far smaller than anything our current machines can resolve. And yet the electron is not nothing. It interacts. It repels other electrons, binds to nuclei, and orbits within atoms. Or rather, it exists in a probability cloud around them. We can trap it in electromagnetic fields and measure its magnetic moment with such precision that it agrees with theory to more than 10 decimal places. In fact, the electron's magnetic moment is the most precisely verified prediction in all of physics. Think about that. We can calculate an abstract number that defines how the electron responds to a magnetic field, and our measurements match theory so perfectly that it's as though nature itself is whispering. Yes, but don't ask me what I am. If you try to see an electron, you run into trouble immediately. Electrons are far smaller than the wavelength of visible light, which means light can't resolve them in the way it can resolve bacteria or even individual atoms. You can bounce higher energy photons, X-rays or gamma rays, off them, but this risks altering the very thing you're trying to observe, like smashing a watch with a hammer to find out how it ticks. Electron microscopes, ironically, don't image electrons themselves. They use electrons as probes to map out larger structures, like the arrangement of atoms in a crystal. The electron is the tool, never the subject. Physicists have tried more exotic methods. Penning traps, for example, use magnetic and electric fields to confine a single electron in a vacuum, holding it in place for months or even years. In these traps, scientists can measure its oscillations, its spin flips, even watch it emit photons as it interacts with fields. But even here, what they observe is not a picture of an electron, but the aftershocks of its invisible presence. The more we chase the electron, the more it behaves like a will-o'-the-wisp, leaving only perfect mathematical footprints in the sand.
This is where quantum electrodynamics, QED, entered the story in the mid-20th century. In QED, the electron is treated not as a tiny billiard ball, but as an excitation of a quantum field that exists everywhere in space. In this view, the electron you think you see is simply the local manifestation of a field that extends across the universe. It is like a ripple on a pond. The ripple is here, but the water it disturbs is everywhere. When you measure an electron's magnetic moment or observe its scattering, you are not measuring a little object. You are measuring the behavior of the underlying field, shaped by the rules of quantum mechanics and special relativity. This field-based view neatly explains why the electron seems point-like. It has no physical size because it is not a lump of matter at all. It is an excitation, a change, in something more fundamental. But this explanation raises its own unsettling question. If the electron is just a ripple in an invisible ocean of energy, is it even meaningful to talk about it as real in the sense we mean for chairs, trees, or planets? When we fire electrons at each other in accelerators, we are really probing the electron field, causing ripples that briefly interact before resuming their eternal rest. When we say we've seen an electron in a detector, what we've actually recorded is the release of energy when the field's excitation interacts with something else. The electron itself, if such a phrase even makes sense, remains hidden, its essence never quite touched. And yet this elusive entity defines the structure of our universe. It shapes the periodic table. It powers the sun through nuclear fusion. It courses through your nerves every time you think, move, or speak. Your very ability to wonder about electrons is mediated by electrons firing in your brain. That is the paradox. The most precisely understood building block in physics is also the most mysterious. We know its mass to a precision of better than 1 part in a billion. We can predict its behavior in magnetic fields, its scattering cross-sections, even its contribution to the stability of matter. And yet when we ask what it is, we find ourselves staring into a mathematical abyss. The harder we look, the less thing-like it becomes. If this sounds unsettling, it is. But it is also a clue, one that will lead us into an even deeper layer of understanding, where the electron ceases to be a particle in any familiar sense and becomes something stranger still, a vibration in the invisible fabric of reality itself. In the next part, we will step fully into that vision, exploring quantum field theory and the idea that the electron is just one ripple in a vast cosmic sea, a sea whose existence changes everything we thought we knew about what is real. Imagine for a moment that you are looking at the ocean from high above. You see the swell of waves, the white caps breaking, the patterns of ripples spreading out from where a stone has been dropped. Now imagine that you have no awareness of the water itself, only the disturbances. You might think that the waves are the thing, the fundamental object. But in truth, they are just fleeting patterns in something deeper, something continuous. This is how quantum field theory tells us we have been thinking about electrons. The leap from particles to fields began in earnest in the mid-20th century, when physicists realized that quantum mechanics and special relativity had to be woven together. In this new framework, every particle is the visible crest of an invisible, omnipresent field. There is an electron field, a photon field, a quark field, each one filling all of space all the time. An electron in this picture is not a tiny marble moving through emptiness. It is a ripple, a localized excitation of the electron field.
And just as ocean waves can appear anywhere there is water, electrons can appear anywhere in the universe because the electron field is everywhere. This idea is more than an elegant metaphor. It solves a number of puzzles that haunted earlier theories. The electron's point-like nature. It makes perfect sense if what we are measuring is not an object with a surface, but a disturbance in a continuous medium. The electron's identical behavior everywhere in the universe. That too follows naturally. Every ripple in the electron field is identical by definition because they are all excitations of the same underlying entity. In quantum field theory, the properties we associate with the electron, its mass, charge, and spin, are built into the structure of the field itself. They are not attributes of a thing, but characteristics of how the field responds when excited. This is where the standard model of particle physics takes the stage. The electron field is one of many in this grand interlocking framework, each with its own particle excitations. Some, like the quark fields, build up the protons and neutrons in atomic nuclei. Others, like the photon field, mediate forces. The electron field is responsible for the negatively charged particles that orbit nuclei, bind atoms into molecules, and make chemistry possible. In this view, when two electrons repel each other, they are not directly pushing on solid bodies. Instead, the electron field and the photon field are interacting. The repulsion is the result of virtual photons, transient disturbances in the photon field, flickering between the ripples in the electron field. The whole drama is an interplay of invisible fabrics, with particles as the fleeting characters that emerge from it. Even the so-called empty vacuum is alive with activity in this picture. The electron field is never truly at rest. It seethes with virtual particles, short-lived excitations that appear and vanish in accordance with the uncertainty principle. This quantum vacuum is anything but empty. It is a restless ocean of potentiality, its fluctuations measurable and, in some cases, exploitable.
This is not just theoretical poetry. Quantum electrodynamics, the branch of quantum field theory dealing with electrons and photons, is the most accurate theory in the history of science. It predicts the electron's magnetic moment to better than 1 part in a trillion, and experiment confirms it with the same precision. The match between theory and observation is so perfect that it is almost eerie, as if the mathematics were not merely describing the universe, but being the universe. And yet, for all its success, this field-based view raises a troubling question. If the electron is just an excitation of a field, is it really meaningful to think of it as a particle at all? Or is particle merely a convenient illusion that emerges when the ripple is localized enough for us to interact with it in a definite way? In everyday life, we deal with electrons as though they were tangible objects, the moving charges in an electrical circuit, the bits of matter in a cathode ray tube, the projectiles in a particle accelerator. But in quantum field theory, these are simply instances of the electron field taking on a particular form in a particular place and time. The reality is the field, the electron is the event. There is something humbling about this. You and I, our bodies, our thoughts, the devices through which you hear these words, are built from patterns in fields that span the cosmos. The electrons in your hand and the electrons in the furthest galaxy are not just similar. They are manifestations of the same field, vibrating in harmony across unimaginable distances. The philosophical implications are hard to ignore. If everything is an excitation of a universal field, then in a sense everything is already connected, not in a mystical, sentimental way, but in the cold, mathematical sense that we are all woven from the same invisible cloth. The separations we perceive are real for practical purposes, but at the deepest level, there is only the field. And the electron, elusive and unpin-downable in older pictures, becomes almost serene in this one. It is no longer a rogue particle darting through the void, but a manifestation of a timeless, spaceless structure. It doesn't need to exist in the way a pebble exists. It exists because the field exists.
Of course, this understanding has not closed the book on the electron's mysteries. Quantum field theory itself rests on assumptions, like the nature of space-time and the constancy of the fields, that may one day be overturned. There are hints from experiments and from the unresolved tensions between quantum mechanics and gravity that the fields themselves may be emergent phenomena arising from something even more fundamental. But for now, the field theory of the electron remains our most complete description. It is precise enough to guide our technology, flexible enough to match every observation, and strange enough to keep philosophers awake at night. Still, even in this majestic framework, the electron has one more trick to play. The vacuum that surrounds it, the empty space in which its field lives, is not passive. It is teeming with invisible actors, fleeting particles that appear and vanish, subtly influencing the electron's properties. In the next part, we step into that invisible theater, the world of virtual electrons and the restless quantum vacuum, where reality bubbles with activity even in its quietest moments. When we imagine empty space, we tend to picture a perfect nothingness, silent, still and inert. But in the quantum world, there is no such thing as empty. The vacuum is alive. In quantum field theory, the electron field, like every field, can never truly be at rest. Even in its lowest energy state, it vibrates with fluctuations. These fluctuations are not random noise. They are baked into the mathematics of quantum mechanics. And from them, something astonishing happens. Particles appear. Not permanent particles like the electrons in atoms, but virtual particles, ephemeral blips that spring into existence, interact for the briefest instant, and then vanish again. They are allowed to exist only by borrowing energy from the vacuum, a loan that must be repaid in accordance with the uncertainty principle. The shorter their existence, the more energy they can borrow. The vacuum, then, is less like an empty stage and more like a crowded marketplace, invisible to the naked eye, but bustling with activity beneath the surface. And for the electron, this marketplace is home. An electron is never truly alone. Even in deep space, far from any atom or beamline, it is surrounded by a cloud of virtual particles, photons, other electrons, and their antimatter counterparts, positrons, all constantly flickering in and out of existence. These companions are not mere decoration. They affect the electron's measurable properties in profound ways. One example is vacuum polarization. The electron's negative charge attracts virtual positrons and repels virtual electrons in the vacuum. This creates a kind of shielding effect, altering the strength of the electron's charge depending on how closely you probe it. At long distances, the shielding makes the electron's charge appear slightly weaker. At extremely short distances, you penetrate the cloud and see the full strength. Another is the electron's anomalous magnetic moment, the tiny deviation from the magnetic strength predicted by the simplest version of quantum mechanics. This deviation is entirely due to the electron's interaction with its virtual entourage. It is here that quantum electrodynamics earns its reputation. The theory's prediction for this value matches experiment to within 1 part in a trillion, making it the most precisely tested agreement between theory and observation in human history. To appreciate how surreal this is, consider the scale. We are talking about effects that occur in time intervals so short they defy comprehension, a billionth of a billionth of a billionth of a second. And yet they leave measurable fingerprints on the electron that we can detect with laboratory instruments. The vacuum is not just a background, it is an active participant in shaping the properties of matter. And it gets stranger. The vacuum fluctuations are not limited to virtual electrons and photons. They can involve any particle allowed by the laws of physics, including massive ones that cannot exist in the real world at low energies. For a fleeting moment, the vacuum can conjure them into being, let them interact, and then reclaim them. This means that in principle the electron is in constant contact with the entire zoo of fundamental particles, all through the medium of the quantum vacuum. From a certain point of view, the electron you think you know, the one with a certain mass, a certain charge, is not a single entity at all. It is the bare electron plus the ever-changing storm of virtual particles that surround it. In this sense, the real electron is not a lone particle, but a dynamic system whose boundaries blur into the fabric of space itself. There are experiments that make this reality impossible to ignore. The Lamb shift, for example, is a tiny difference in the energy levels of hydrogen atoms that cannot be explained without accounting for the electron's interaction with vacuum fluctuations. Likewise, the Casimir effect, a force that arises between two metal plates placed very close together, is a macroscopic manifestation of the vacuum's restless energy. These are not fringe phenomena. They are mainstream, measurable consequences of a vacuum that never sleeps. And yet, for all its activity, the quantum vacuum is an elusive thing to define. In some interpretations, the vacuum is the ground state of all fields, the lowest possible energy configuration. In others, it is a seething foam of quantum uncertainty, perhaps even connected to the structure of space-time itself. If the latter is true, then the behavior of the electron's virtual companions might be a faint whisper of the deeper laws that govern the universe. Physicists suspect that the vacuum could hold the key to some of our greatest unsolved mysteries. The cosmological constant, the tiny energy density of the vacuum that drives the acceleration of the universe's expansion, is predicted by quantum field theory to be vastly larger than what we observe. The mismatch between theory and reality here is so extreme that it has been called the worst prediction in physics. Somewhere, there is a piece of the puzzle we don't yet understand. This uncertainty opens the door to speculation. Some suggest that the vacuum's energy is not fixed but dynamic, that it could change under extreme conditions, rewriting the rules of particle physics in the process. Others propose that what we call virtual particles are actually real, but exist in a domain beyond our usual space-time, appearing and vanishing in our view as they move in and out of our observable reality. Whatever the truth, one fact remains. The electron is inseparable from its vacuum environment. The idea of a bare, isolated electron is as fictional as an isolated ripple in an ocean without water. The two cannot be divorced. And this brings us to a deeper realization. If the vacuum shapes the electron and the electron shapes matter, then the vacuum, this invisible, restless sea, shapes everything. The stability of atoms, the chemistry of life, the function of your brain, the light from the stars, all depend on the ceaseless, unseen dance of virtual particles in empty space. The question is no longer, what is the electron, but what is the stage on which it performs? To answer that, we must look at the experiments that have tried to push the electron to its limits, to see if, under the right conditions, it might reveal cracks in our theories or hints of new physics. In these tests, the electron becomes not just a subject of study, but a messenger from the deeper layers of reality. If the electron were merely an obedient cog in nature's machinery, our story might have ended decades ago. But every time we think we understand it, someone finds a new way to put it on trial, and the results keep pulling us deeper into the unknown. One of the earliest surprises came from the Stern-Gerlach experiment, though it was originally performed on silver atoms. In 1922, Otto Stern and Walter Gerlach sent a beam of silver atoms through a non-uniform magnetic field. Classically, you'd expect the magnetic moments of the atoms to be randomly oriented, producing a continuous spread on the detector screen. But instead, the beam split cleanly into two spots, as if the magnetic moment could only take on one of two discrete values. This phenomenon, later understood as spin quantization, applies to electrons as well. The electron's spin, a quantum property not to be confused with literal rotation, can only be up or down relative to a chosen axis. There is no in-between. This is a deeply non-classical behavior, a sign that electrons are not tiny spinning balls, but something more abstract, something whose orientation is an intrinsic quantum state. Then there was electron diffraction. Building on de Broglie's hypothesis that matter behaves like waves, experiments in the late 1920s sent beams of electrons through crystalline materials. The electrons scattered in patterns identical to those of X-ray light waves, bright and dark fringes caused by interference. This was the experimental nail in the coffin for the idea of electrons as purely particles. They were undeniably wave-like, but only when not being measured for their which-path information. If these experiments confirmed the quantum view, others would push its philosophical boundaries. In the 1960s, physicist John Bell derived Bell's theorem, a mathematical inequality that any local hidden variable theory must satisfy. Quantum mechanics predicts that in certain entangled systems, these inequalities will be violated. And when experimentalists put it to the test, using entangled electrons and photons, the violations appeared exactly as quantum theory predicted. This was devastating for Einstein's dream of a deeper, deterministic theory that preserved local realism. The idea that properties exist before they are measured, and that no influence can travel faster than light. Electrons entangled with each other could exhibit correlations that defied classical explanation, even when separated by vast distances. It seemed to confirm the unsettling idea that quantum reality is non-local, that parts of the universe can remain mysteriously linked in ways our everyday experience cannot explain. The electron also played a starring role in tests of quantum tunneling, the ability of particles to pass through energy barriers they shouldn't have enough energy to overcome. In the quantum picture, the electron's wave function extends into classically forbidden regions, allowing it to leak through barriers. This isn't just theoretical. Tunneling underpins technologies like flash memory, scanning tunneling microscopes, and even nuclear fusion in stars. Every time an electron tunnels, it is a reminder that quantum mechanics is less about solid objects moving along predictable paths and more about probabilities seeping through the edges of possibility. More recently, precision measurements of the electron's magnetic moment and electric dipole moment have kept physicists on edge. The magnetic moment, as predicted by quantum electrodynamics, matches experiment with exquisite accuracy. This agreement is so perfect that any deviation could signal the presence of new particles or forces, hints of physics beyond the standard model. The electric dipole moment, on the other hand, is expected to be vanishingly small. If the electron were perfectly spherical in its charge distribution, it would be exactly zero. But if new physics, such as undiscovered heavy particles, exists, it could give the electron a tiny asymmetry, making it slightly egg-shaped at the quantum scale. So far, every increasingly sensitive search has found nothing, but the hunt continues. Each null result tightens the constraints on theories of supersymmetry, dark matter, and other speculative realms. And then there's the quantum Zeno effect, a phenomenon where the act of observing a quantum system frequently enough can freeze its evolution. In experiments involving trapped electrons, repeated measurements can effectively hold the particle in its initial state, preventing it from transitioning as it otherwise would. It's as if the electron responds to our persistent gaze by refusing to move, a counterintuitive outcome that blurs the line between measurement and manipulation. Even the double-slit experiment refuses to be exhausted. Variations now use electrons entangled with other systems, delayed choice measurements, or weak measurements that try to peek at the electron's behavior without collapsing its wave function. Each new twist seems to reinforce the same strange message. The electron is not a thing that moves through space in a single fixed way. It is a participant in a process that only crystallizes into a definite outcome when certain conditions, often tied to the availability of information, are met. What all these experiments share is a refusal to grant us the simple comfort of a fixed identity for the electron. In one test, it's a wave. In another, a particle. Sometimes it acts as if it knows about measurements that haven't yet been made. Sometimes it seems to coordinate with a partner across vast distances instantly. Sometimes it's a ghost slipping through barriers. Sometimes it's a stubborn prisoner held in place by our scrutiny. The cumulative effect is hard to overstate. The electron is no longer a humble building block in the classical sense. It is a shapeshifter, a manifestation of underlying rules that defy the categories we use for the macroscopic world. The experiments tell us that those categories, particle, wave, path, position, are conveniences, not truths. And yet, even with all this strangeness, the electron remains indispensable. Remove it from our equations, and atoms collapse. Remove it from our technologies, and civilization as we know it ceases to function. Remove it from the chemical bonds in your DNA, and you vanish. The experiments, then, are not just about probing an odd little particle. They are about asking whether reality itself is a fixed, pre-existing structure or an unfolding set of possibilities. And the electron, obligingly or mischievously, continues to give answers that keep both possibilities alive. In the next part, we'll step away from the laboratory for a moment and into the philosophical abyss, the interpretations of quantum mechanics that try and fail to tell us what the electron really is when we're not looking. If physics were just about predicting the results of experiments, our story of the electron could end here, neatly wrapped in the mathematics of quantum field theory. But the human mind isn't satisfied with prediction alone. We want to know what it means. What exactly is the electron when we're not looking? Here, physics crosses the border into philosophy, and the landscape becomes a minefield. The first divide is between realism and instrumentalism. Realists believe the electron exists as a definite entity with properties, whether or not we measure them. The equations describe something out there in the world. Instrumentalists, by contrast, see those equations as tools for predicting observations, nothing more. The electron, in this view, is not an object. It is a convenient story we tell to organize our experiences. Niels Bohr leaned toward the instrumentalist side. He argued that asking about an electron's position before measurement was like asking about the path of a rainbow. It has no reality outside the conditions that produce it. Albert Einstein, ever the realist, resisted fiercely. "I cannot believe that God plays dice with the universe." For Einstein, the electron's apparent indeterminacy was a symptom of incomplete knowledge, not a feature of reality itself. Then came Hugh Everett and his many worlds interpretation. Instead of the wave function collapsing when measured, Everett proposed that all possible outcomes of a quantum event happen, but in separate branching universes. In one branch, the electron goes through the left slit, in another, the right. In one, its spin is up, in another, down. We perceive only one branch because we too are part of the branching. This idea neatly preserves realism. The wave function is real and nothing truly disappears, but at a cost. It implies an unfathomable proliferation of universes, all equally real, all constantly splitting. For some, this is elegant. For others, it's an extravagant solution that replaces one mystery with 100 more. Another approach, pilot wave theory or de Broglie-Bohm theory, restores determinism by giving the electron a definite position at all times, guided by a pilot wave that evolves according to the Schrodinger equation. In this view, the interference pattern in the double-slit experiment is not because the electron is in many places at once, but because the guiding wave is, and the electron follows its contours like a surfer riding a swell. Pilot wave theory explains quantum phenomena without the need for collapse, but it introduces non-locality, the idea that the pilot wave can instantaneously influence the electron's behavior, no matter how far apart they are. This clashes with relativity's speed limit, though proponents argue the influence cannot be used to send messages faster than light. Then there's relational quantum mechanics, which goes further still. It proposes that properties like an electron's position or momentum exist only in relation to an observer. There is no absolute state of the electron, only the outcomes of interactions between systems. In this view, the electron's reality is not a fixed thing, but a web of relationships that depends on context. All of these interpretations are consistent with the experimental data. None can be disproven by current evidence, and that's the maddening part. They tell utterly different stories about what is really happening, yet they all produce the same measurable results. Which leaves us with a disquieting possibility. Maybe the universe doesn't owe us a single intuitive narrative. Maybe the electron resists definition, not because we're missing the right picture, but because no single picture exists. This brings us back to the concept of superposition. Before measurement, the electron is in all possible states, not as a ghostly particle smeared through space, but as a probability amplitude that encodes every potential outcome. The act of measurement doesn't just reveal the state, it creates it. For a realist, this is deeply unsatisfying. It makes reality feel contingent, as if the universe is playing a game of make it up as you go. For an instrumentalist, it's liberating. We can stop asking unanswerable questions about the true state of the electron and focus on what we can actually measure. But both views face a common, unspoken problem. The human brain evolved to navigate a macroscopic world of rocks, rivers, and predators, not a probabilistic realm where objects blur into waves of possibility. Our intuition insists that the electron must be something concrete, even if our equations say otherwise. The philosopher of science David Mermin once summed it up with a provocative line, "Shut up and calculate." His point was not to belittle curiosity, but to acknowledge that for now, the mathematics is the most complete expression of our knowledge. The stories we tell about the electron, whether as a particle, a wave, a ripple in a field, or a branching set of possibilities, are human translations of that mathematics, each with its own compromises. And yet, the philosophical stakes are enormous. If the electron has no definite properties until measured, then reality itself is not a fixed, pre-existing stage, but an emergent phenomenon, a conversation between the universe and the observer. If, on the other hand, the electron is always definite, guided by hidden variables or existing in multiple worlds, then our role in the cosmic story is far smaller, and the quantum strangeness is an illusion born of our limited perspective. Either way, the electron refuses to be just another entry in a particle catalogue. It is a mirror in which we see both the power and the limits of human understanding. And the deeper we stare into that mirror, the more it stares back, reflecting our assumptions, our biases, and our hunger for certainty. But philosophy alone cannot decide the matter. The next great leap in our understanding of the electron will come from new experiments, new technologies, and perhaps entirely new physics, tools sharp enough to cut through the fog that has surrounded this particle for more than a century. Before we look forward to that frontier, we must take stock of why the electron matters so deeply in the first place, not just to physics, but to everything. Because without the electron, there would be no chemistry, no biology, no light, no life. And in understanding that role, we may find clues to the deeper truth we've been chasing all along. For more than a century, the electron has been the loyal workhorse of science and technology, running through our circuits, glowing in our screens, and holding our atoms together. Yet, for all its practical uses, it remains one of the deepest mysteries in physics. The question is, will the 21st century finally bring us closer to knowing what it really is? The search begins with precision measurements. The electron's magnetic moment, that slight tilt in its response to a magnetic field, has already been measured to 1 part in a trillion. The match with quantum electrodynamics is so perfect that any deviation would be a flashing neon sign pointing to new physics. Physicists are building experiments even more sensitive than today's record holders, hoping to find a crack in the facade. Then there's the hunt for the electric dipole moment, EDM of the electron. If the electron's charge distribution were slightly asymmetrical, it could signal the presence of undiscovered particles or forces, possibly connected to why the universe contains more matter than antimatter. Current experiments have found no EDM, but the limits are tightening, closing in on the predictions of certain beyond the standard model theories. If the EDM is ever found, it will upend our understanding of particle physics overnight. Another promising avenue is the search for electron substructure. Quantum field theory treats the electron as fundamental without internal parts. But what if that's wrong? High-energy colliders like CERN's Large Electron Positron Collider and its successors have probed electrons down to unimaginably small scales, finding no hint of smaller components. Still, new collider designs, capable of energies many times greater, could reveal substructure just as higher energies once revealed that protons are made of quarks. The electron also plays a starring role in experiments probing the foundations of quantum mechanics. Tabletop tests with trapped electrons or electron interference patterns might uncover subtle deviations from quantum predictions, hinting at a more fundamental theory beneath. Some researchers are even exploring whether gravity could cause wave function collapse at certain scales, a radical idea that could connect the quantum world to Einstein's general relativity. Speaking of gravity, the electron may yet prove to be a messenger between the known and the unknown. We still don't know how gravity interacts with quantum particles in detail. Testing how electrons behave in strong gravitational fields, near black holes or in ultra-precise Earth-based experiments, could reveal hints about quantum gravity, the long-sought unification of Einstein's and Schrödinger's visions. There's also the tantalizing possibility that electrons could help solve the mystery of dark matter. Some dark matter models predict interactions with electrons that are too weak to be noticed in everyday life but could be teased out in specialized detectors. A faint scattering signal, or an unexpected pattern in the cosmic microwave background, might one day tell us that the electron has been whispering to a hidden sector of the universe all along. In the realm of technology, the electron is already central to the most ambitious frontier of computation, quantum computing. Qubits based on the spin of single electrons, trapped in quantum dots or defects in diamond, could become the building blocks of machines that outpace classical supercomputers. Studying electrons in these contexts isn't just about building better devices, it's about probing their quantum nature in the most controlled environments ever created. And then there's the possibility of entirely new experimental geometries. Electron interferometers are being designed with unprecedented stability and isolation, capable of performing delayed choice experiments at scales never before attempted. These could force us to confront whether the electron's wave really exists everywhere at once, or whether some deeper process underlies its interference patterns. Beyond the lab, astronomers are finding that electrons play unexpected roles in some of the most extreme environments in the universe. In pulsars, magnetars, and the coronae of black holes, electrons are accelerated to energies billions of times higher than anything we can produce on Earth. Studying their radiation offers a way to test fundamental physics under conditions no human-built machine can replicate. If electrons behave differently in these cosmic laboratories, it could hint at new laws waiting to be uncovered. Theoretical physics, meanwhile, is grappling with the possibility that the electron is not truly fundamental, but an emergent phenomenon. Some approaches to quantum gravity, including certain interpretations of string theory, suggest that particles like the electron could be excitations of even more basic entities, such as one-dimensional strings or networks of space-time geometry. In these pictures, the electron, as we know it, is a convenient label for something much more exotic. And there's a more radical possibility still, that the electron is only real in the same way a shadow is real. In the holographic principle, our universe could be a projection from information encoded on a lower dimensional surface. In such a reality, electrons are not self-contained objects, but manifestations of information processing on a cosmic scale. What's striking about all these avenues, from precision measurements to cosmology to quantum gravity, is that the electron sits at the crossroads of everyone. It is the particle we know most about, and yet it is the one most likely to expose the limits of our knowledge. If history is any guide, the future of the electron will not be a slow accumulation of details, but a series of revolutions. The discovery of its true nature could rewrite the standard model, force us to rethink the role of the observer in quantum mechanics, or even change our definition of what it means for something to exist. The stakes are not just scientific but philosophical. To know the electron is to know the rules of the smallest building blocks of reality, and perhaps to discover that those rules are not fixed but fluid, changing with the scale at which we ask the question. And if that happens, we may look back at the electron not as a thing at all, but as the first crack through which the deeper light of the universe began to shine. Next, we'll step away from pure theory and hard experiments to look at the human connection, how this elusive particle shapes our bodies, our technologies, and the very conditions for life, and why our relationship with it is as intimate as it is mysterious. We often speak of the electron as though it belongs to the rarefied realm of laboratories, chalkboards, and particle accelerators. But in truth, it is with us always. Every breath, every heartbeat, every flicker of thought in your mind is an electron in motion. The electron is not just a character in the story of the universe. It is the ink in which the story is written. Consider your own body. The atoms that make up your cells are held together by electromagnetism, a force mediated by the interplay between electrons and protons. Without electrons orbiting nuclei, or more accurately existing in their probability clouds, there would be no chemical bonds. Hydrogen and oxygen would never combine to make water. Carbon could not form its vast network of molecular architectures. Proteins would not fold, DNA would not twist, and life would remain an unfulfilled possibility. At the most intimate scale, electrons are the gatekeepers of biochemistry. Enzymes work by guiding electrons through specific pathways, breaking and forming chemical bonds with surgical precision. Photosynthesis, the process that powers nearly all life on Earth, is, at its heart, an electron transport chain, shuttling these particles between molecules to store the energy of sunlight in chemical form. Even your thoughts are electron dances. Neurons communicate through electrical impulses, which are themselves the coordinated movement of electrons and ions across membranes. Every sensation you've ever felt, every memory you've ever made, is a choreography of electrons, billions of them moving in patterns shaped by experience, biology, and time. Our relationship with electrons extends far beyond biology. They are the lifeblood of technology, the electrical grid that lights our cities, the batteries that power our devices, the circuits that process our words and images. All of it is nothing more than the controlled flow of electrons. The term electronics is not a coincidence. It is a direct admission that this one particle is the foundation of our technological civilization. When you flip a light switch, you set off a cascade of electrons moving through copper wires, colliding with atoms, releasing photons that brighten a room. When you open your phone, electrons race through silicon pathways, each pathway engineered to guide them with the precision of a watchmaker's gears. The Internet itself, this invisible network of voices, images, and ideas, is a web spun from electrons, leaping across fibers and satellites in a planetary ballet. But the electron's influence goes even further. In the stars, electrons help govern the processes that create the elements of the periodic table. In the crushing heat and pressure of stellar cores, electrons and protons merge to form neutrons, a step in the creation of heavier nuclei. Without electrons behaving as they do, the universe might contain nothing but hydrogen and helium. No carbon for life, no oxygen to breathe, no iron in your blood. And then there's light. Every beam of sunlight, every flicker of a candle, every star twinkling in the night sky exists because electrons can jump between energy levels in atoms. When an electron drops to a lower energy state, it emits a photon, the particle of light. The colors of a sunset, the green of leaves, the glow of distant galaxies, all are electron signatures, fingerprints in the spectrum of the universe. The irony is that while electrons are the most immediate actors in our daily reality, they are also the least tangible. You have never seen one, you never will. yet without them, you would not exist to wonder about them. This is where the scientific and the poetic meet. The same particle that defies our attempts to pin down its true nature also shapes the warmth of a sunrise, the sharpness of a thought, the music of human conversation. The electron is at once alien and familiar, a stranger whose work we recognize everywhere, even as we fail to grasp its essence.
In a sense, our intimacy with electrons is what blinds us to their mystery. They are so woven into the fabric of our existence that we mistake them for something ordinary. We think of them the way we think of the air, present, reliable, invisible, until, like air, we are reminded that it is not an emptiness but a substance, full of motion and complexity.
There's also a humbling thought here. When you touch another person's hand, your skin never truly makes contact with theirs. What you feel is the repulsion between the electrons in your atoms and the electrons in theirs. Physical contact is, in fact, an electromagnetic negotiation between two quantum systems. Every hug, handshake, or brush of fingers is mediated by the quiet insistence of electrons that no two of them can occupy the same state in the same place. The Pauli exclusion principle in action, expressed not in equations, but in the human experience of touch.
Electrons are, quite literally, the interface between the tangible and the intangible. They bridge the gap between the unseen quantum rules of the microcosm and the vivid sensory world of the macrocosm. Without them, the laws of nature would remain abstract, unexpressed. With them, the universe comes alive.
It is tempting to think of the electron as something we have harnessed, a servant of our will. But the truth is the opposite. Our entire civilization is an intricate improvisation around the behavior of electrons. We have learned to coax them into circuits, persuade them into magnetic storage, and trick them into producing coherent beams of light in lasers. But at every step, we play by their rules. And maybe that's the real connection. We are not separate from the electron's story. We are a chapter in it. The universe formed electrons in the first fractions of a second after the Big Bang. Those electrons joined protons to form atoms. Those atoms clumped into stars. Those stars forged heavier elements, and those elements became the raw material for life. We are the inheritors of an unbroken chain of electron interactions stretching back 13.8 billion years. In that sense, every time we ask, "What is an electron?" we are also asking, "What am I?" In the next and final part, we will return to the deepest mystery. Whether the electron, for all its familiarity, is truly real in the way we imagine, or whether it is an intricate illusion woven by the mathematics of the quantum world. And we will close with the only ending such a journey can have, one that leaves the question alive. We began with a simple premise: the electron is everywhere. It lights our cities, fuels our devices, shapes our bodies, and holds the matter of the universe together. It is the currency of technology, the architect of chemistry, the painter of light. And yet, after more than a century of experiments, equations, and revolutions in thought, we still cannot answer with complete honesty the question that started this journey. What is an electron? Is it a particle? A discrete dot in space? Sometimes, in the right experiment, the electron hits the detector as a single point, leaving a mark as sharp and final as a raindrop on stone. Is it a wave? Without a doubt. In the double-slit experiment, it interferes with itself, weaving bright and dark fringes as though it exists in many places at once. Is it a ripple in an invisible field? Quantum field theory says yes. A localized excitation of a universal electron field, identical everywhere in the cosmos. Or is it something stranger still, an expression of probabilities until the moment of measurement, a story told only when an observer enters the scene? Each answer is true, and each answer is incomplete. The deeper truth is that the electron resists our categories because those categories were forged in a world of stones and rivers, not in the subatomic realm where possibility outweighs certainty. It is as if the electron is not a thing in the sense we understand, but a process, a set of relationships, interactions, and outcomes that, taken together, give the illusion of an object. We have learned to live with this ambiguity. Physicists shut up and calculate, engineers build devices without needing to know the metaphysics, and philosophers argue endlessly over what the equations mean. But the question lingers, stubborn as ever. Does the electron exist independently of our measurement, or is it conjured into being by the very act of asking? The most unsettling possibility is that reality itself is like the electron, not fixed, but emergent. That the universe, at its most fundamental level, is a shifting network of probabilities, solidifying only when certain conditions are met. That what we call real is simply what has survived the filtering of observation. If so, then the electron is more than just a building block of matter. It is a glimpse into the machinery of reality-making itself. It is a hint that the universe is not a pre-written script, but an improvisation, one in which we, by observing, are also performing. And yet, for all this strangeness, the electron remains the most familiar of companions. Every second of your life, trillions of them are at work inside you, in perfect, unthinking harmony. They leap between molecules in your brain to fire a thought. They flow through the metal in your headphones to deliver music. They burst from the sun, travel 93 million miles, and strike your skin as warmth. Perhaps this is why the question of their reality strikes so deeply. The electron is both utterly alien and intimately ours. To question it is to question ourselves, our place in the universe, our trust in what we see, our definition of real. And maybe the truth is that the electron is real enough to bind atoms, to power our tools, to carry life forward. Real enough that, even if its essence lies forever beyond our grasp, its effects are undeniable. Still, there's a certain poetry in not knowing. If the electron had yielded all its secrets by now, the mystery would be gone, and with it, a piece of the wonder that drives science itself. The unknown is not a failure. It is the open door through which discovery walks. So we end where we began, with a particle we can never quite pin down. A particle that is a wave, that is a ripple, that is a possibility, that is perhaps a question in disguise. Somewhere, right now, an electron is leaping from one atom to another, lighting a filament or sparking a signal through your nervous system. You will never see it, you will never hold it. But without it, there would be no you, no me, no stars, no story to tell. Perhaps that is the answer, not in the equations, but in the fact that we are here at all. And perhaps the electron is real precisely because it refuses to be anything less than mysterious. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.